Good morning, ladies and gentlemen. May I have your attention, please? Thank you. Let's go ahead and get started. So, how did we integrate that first one? That first one when we had the indefinite integral of 1 over x squared plus 1. How did you recognize that? Sammy?
Tangent inverse.
Absolutely. This is a straight inverse tangent problem, and so we don't have to provide any constants for that one. All right, let's take a look at the second one. In the second one, we have an x on top, and that changes our approach dramatically. So how did you handle that second one then? Kobe?
I did a natural log of x squared plus 1 over 2.
Absolutely. And so the second one, because that x on top, right, we've got two distinct pieces, it's acting as part of the derivative of this quantity on the bottom, all to the first power, which makes it a candidate for natural log, so long as the derivative of that quantity exists. In fact, if we had a 2x there, right, we know that this would integrate straight to a natural log of absolute value of x squared plus 1. Now, the bars aren't necessary here, right, but it's habit when we integrate into a natural log function to include the bars on my input. And then we didn't have the 2 there. And so how do we account for that? Well, we'll need to cancel out that derivative of the inner quantity if we were to differentiate with a 1/2. Go ahead and raise your hand if you first had inverse tangent, which I didn't check yet. Inverse tangent for number 1. Yes. Number 2, raise your hand again. 1/2 natural log of. Close bars, some of you? Okay, so we're going to have to be able to integrate things like this and more today as we algebraically manipulate expressions so that we're recognizing what rule they come from. Number 3, how could we handle that? Well, gosh, that's a lot like number 2, but completely different, right? The flipping of the numerator and denominator means that that x is no longer a part of the derivative of that quantity, right? X squared plus 1, because it's 1 over x now. So what do we do? Well, how do you handle this? Anybody want to share, Riley?
I broke up the fraction and then integrated each part individually.
Nice job. So Riley recognized that we could break up a sum or difference in the numerator of a fraction, right, into a sum or difference of separate fractions, each with the same denominator. And that's the way to handle that sum or difference in the numerator of this rational function. So here we went x squared over x plus 1 over x, which means we can now integrate term by term, right? This is just the integral of x plus the integral of 1 over x, and we can now integrate term by term. So it looks like x squared over 2 plus c, but I'll hold off on that until we get our second part. Natural log of absolute value of x, close bars, plus c. Put it all together. Raise your hand if you got as far as Riley. So anybody get to the x squared over 2? So break up this. Way to go, you guys. Awesome. What questions do you guys have about today's Bellwork? Okay, then let's go ahead and take care of our homework check. We've got 2 different checks to do, and I'll pause the recording. Okay, ladies and gentlemen, let's go ahead and take a look at our end of the year schedule. So today, the 16th, we'll be grappling with some integrands that need to be algebraically rearranged so that we can recognize one of the rules we already have. Next class, on the 18th, we'll be developing a brand new technique, typically seen in Calc 2 courses across the country. Integration by parts is going to be able to handle, right, undoing a product that's in the integrand. So while we have a product rule for differentiation, we do not yet have one for integration. We're going to develop that and then apply it next class for our last day of new learning. It'll be a final red mark, so we'll be all set for our Bellwork and activity stamp check. After those are collected, I can put those in Infinite Campus, right? After I've gotten that from everyone in both classes. And then you'll get the multiple choice 2008 Part A. That's going to work as your review for Part 1 of the final exam. On the 20th, we'll have a structured review day. For those of you who are going on the physics trip, right, you won't be missing any new learning. It's just going to be work time during that day for you to correct your multiple choice Part A and work on multiple choice Part B. Then, on Tuesday, the 25th, you'll be taking your final exam, Part 1. That is Tuesday, isn't it? Oh, that's Wednesday. So that's, okay, so Wednesday, the 25th, you'll be taking Part 1. That is multiple choice part A, non-calculator. You're very familiar with it. It'll be AP format. Then on the designated senior final exam day, the 27th, you'll be taking the second and final part of your final exam. That is the part B, calculator allowed multiple choice. It'll be exactly the same. It'll be a previous AP exam multiple choice section only. There won't be free response for this portion of the for the final exam. The same scale conversion will be used, however, to arrive at your test grade in the class. And so I'll be taking your multiple choice score, the weight factor, and then doubling it. And then I'll use the conversion scale to move it to your unit test grade. So it'll be just like your unit test AP practice before the actual exam. Everybody remember that? Awesome. Questions about the end of the year? We're all set up then, so make sure that you have all your activities and your red marks and stuff for next time so we can get that going in the campus. Great. So how are these similar? How are these different? Right? Go ahead and check with your partner, come up with the response, because then I'm going to call on you to share with the whole class. So how are these similar? How are they different? How do they change our approach when integrating? So lots of similarities and lots of differences, or some things that you guys talked about. Right? What were some things that were similar, or some things that were different? Emily and Riley?
They all have the x squared plus 1 quantity somewhere in it.
True, absolutely. They all have the x squared plus 1, and that was common throughout. Right? What was the difference? What was the difference? Evie and Joel?
Like when the x squared plus 1 is located within the...
Absolutely. That quantity x squared plus 1 made a difference, whether the quantity was on top or on bottom, right? In terms of being able to rearrange it or break it up as a fraction. So what we're going to look at today is the connection between the different pieces and seeing if we can manipulate that integrand expression, right? So that we can recognize it as one of our previous rules, like inverse tangent or natural log or simply algebraically rearranging, and that's where we're headed today. All right, so what if it had been this? What if we had x squared plus 1 and x squared? Notice the degree of my numerator and denominator now are not separated by, right, 1, such was the case with that x and the x squared plus 1. But if it had been x squared plus 1 over x squared, would that have changed our approach? Well, Riley's approach still clearly would work. We've got a sum or difference in the numerator of a fraction, so I can break that up as a sum or difference of individual fractions. This one is just a straight algebraic rewrite. We'll break up that fraction. So this will become x squared over x squared plus 1 over x squared. A final rewrite. And we're ready to go term by term. So it looks to me like integrating each of these terms in my sum or difference separately produces an antiderivative of x. And then, is the second one natural log now? Or is this natural log? No. Tyler?
No.
No, right? What would this be instead? What rule overall? Absolutely. Because my quantity on bottom is to the second power, this is not a candidate for natural log. Good. So we'll add 1 to the current exponent, which is -2, to get a new exponent of -1. Divide by my new negative exponent is going to produce -1 over x for my antiderivative, and then plus c. Awesome. So that wasn't bad, right? Having the degree same on top and on bottom. What happens if we flip that though? Again, degree 2, but now we have my sum and difference in the bottom of my fraction. Okay, in the bottom of my fraction. So can we break this up? Can we break this fraction up the way we did for 4a? No, that sum or difference in the denominator of fraction can't be broken up, right? That's not the way that fractions work. And so what are we going to do? Well, we can attack this a couple different ways. We could utilize our pre-calculus techniques of polynomial long division, right, to rewrite this. Or we could add a clever 0 to that numerator expression and create a sum or difference, which could then in turn be broken up. the choice is yours. In fact, I'm going to model both ways so that you can choose later on your assignment. One, right, the adding a clever zero is nice and clever, right, but you might not necessarily remember it. And then, so what was the technique that will always work that you can grind it out? That's the polynomial long division. First though, let's do the add a clever zero because that's pretty neat. If I made this x squared on top, right, over x squared plus 1, but then added 1 and subtracted 1, we see that the value of my numerator remains unchanged. That is, x squared plus 1 minus 1 is still my original x squared. We've done nothing to change the value of my original integrand. However, if I now look at this as a sum or difference in terms in top, and group that x squared plus 1 together, I can now break up this difference of two terms in such a way that I produce an integrand that I can handle now using our previous technique. That is to say, group the x squared plus 1, right, together and put that over my denominator, x squared plus 1. Then we have the subtraction for my second term, minus, there's my squiggle underline minus in my grouping. And what's the second term? 1 over x squared plus 1. So by adding a clever zero, we've created now a sum or difference in the numerator of a fraction that I can break up into a sum or difference of individual fractions. So that's pretty smooth. But it's only helpful if it produces integrands for which I now recognize rules. Do I have a rule for that first one? Well, yeah, that's just 1. And do I have a rule for the second one? Deja vu. I feel like I've been here before. Deja vu. I feel like I've been here before. It's Bellwork number 1, right? You know how to handle that. Awesome, blossom. And so now we can go term by term. It looks to me like we get antiderivative for 1 with respect to x, x minus inverse tangent of x plus c. That's pretty sweet. Well, adding a clever zero is fun and kind of clever, right? It's also tricky Ricky. We might not remember it necessarily, right? Because it's sort of one of those clever tricks. And so what will always work? Well, if my degree of the numerator, right, is greater than or equal to the degree of the denominator, we could rewrite by employing polynomial long division. So let's see if I have this again. I don't. So let's go ahead and clone this page quick just so I have enough space. We'll go ahead and clone page and clearing. Love it. And now let's do it with polynomial long division. So recall from pre-calculus, I can use polynomial long division by taking my numerator, in this case x squared, and we're going to divide it by my denominator. So we're going to see how many times x squared plus 1 goes into my numerator x squared. And remember, we just focused on our dominant term in order to do this. And so we asked ourselves the question, x squared times what equals x squared? 1. And then we do top times the side all the way through. And 1 times x squared plus 1 is x squared plus 1. And then what's our next step in our algorithm for long division? After we multiply top times the side all the way through? Subtract, right? So we've got to subtract. And so we subtract x squared minus x squared is 0, and then nothing. 0 minus 1 is -1. And then bring down, but we don't have anything to bring down, and so it looks to me like my remainder, right? My remainder is that -1. What? How in the world does this help me? Well, we've seen that this original integrand, x squared, divided by x squared plus 1 is equal to 1 with a remainder of -1 x squared plus first. That is, we can rewrite my original integrand as 1 plus the -1 x squared plus 1. So 1 minus 1 over x squared plus 1. How How's that helpful? Well, now look at our integrand. We can now integrate term by term, and by golly, that looks familiar. There's our 1 minus 1 over x squared plus 1. So that's pretty smooth. Integrating with respect to x produces an antiderivative of x minus inverse tangent of x plus c. That's pretty sweet. So you can think about which you like better. If you like the adding a clever zero, right, which is kind of tricky Ricky, but clever, or the polynomial long division, which is appropriate for use when my numerator, right, degree is greater than or equal to my denominator degree. Let's take a look at another. Oh my gosh! It looks like my numerator degree is greater than or equal to my denominator degree. So can I break up this fraction? No, that sum or difference occurs in the denominator. I'm not able to break up that fraction into a sum or difference of individual fractions. That's not the way a fraction works, but we certainly can, right, do our polynomial long division. And so clever zero is not going to help here, right, because I won't be able to reduce that top over bottom even if I were to split it up. So let's go ahead and use polynomial long division. We'll make x cubed, and we'll divide it by x squared plus 1. And we'll focus in on our dominant. And we'll say x squared times what equals x cubed. Well, this time x squared times x, is that right? X squared times x equals x cubed, and then top times the side all the way through. So top times the side all the way through would produce x cubed plus x, is that right? Next, we've got subtraction in our algorithm all the way through. So we've got x cubed minus x cubed is 0. And then nothing minus x is minus x. And now x squared goes into x how many times? It goes into negative x how many times? None. So we've reached the end of the road, which means this is my remainder. So it looks like x with the remainder of negative x. What? Well, we can rewrite this now. My original integrand, x cubed over x squared plus 1, as x minus x over x squared plus 1. So we've used polynomial long division so that we can rewrite my original integrand and see now if we can handle it using rules that we already have developed. So what does this equal? It equals x plus a negative x squared plus 1. So I'll write that as negative x over x squared plus 1. Was this algebraic rewrite helpful to us? Well, yeah. Now we can tackle that term by term. We have a rule for this, right? It's our Bellwork number 2. Now, because the degree of my numerator and denominator differ by 1, that numerator can act as the derivative of the quantity on bottom, signaling a natural log, right? A natural log rule. So we can go ahead and now integrate term by term. This will be x squared over 2. If I had, right, if I had the derivative of this quantity on bottom to the first power, this would be a natural log antiderivative rule. Do I have the derivative? No, but I have the important part, the variable part. So what do I need to include here? If I had a 2, right, if I had a 2x, then I could go natural log, but I didn't, so I'll have to include a 1/2 natural log of absolute value bars are unneeded, but I always include them, but I have it, plus c. And so I think we're set. That's pretty sweet. I like that one. What question do you guys have about 5a? So if the degree of my numerator, right, is greater than or equal to my denominator, and I can't split it up into a sum or difference, I'll go ahead and utilize polynomial long division as a means to algebraically rewrite and try again. All right. Go ahead and decide with your partner, do we need to employ polynomial long division to tackle 5b? So do we have to use polynomial long division for this one? Colin and Grace?
No.
No, what can we do instead?
You can split the numerator
Absolutely, because there's no sum or difference in bottom, and there is a sum and difference in top, I could rewrite this as a sum or difference of individual fractions, each with the same denominator, and then try again. So let's go ahead and split that up. It looks like x squared over x cubed plus 1 over x cubed. And now it looks like that'll reduce nicely. This becomes the indefinite integral of quantity 1 over x plus 1 over x cubed. And now we can integrate term by term. And so it looks like my first one, natural log rule, plus c, I'll group with the second one. Not natural log for the second term in my integrand. This will be straight power rule, where my current exponent is -3. So adding 1 to my current exponent, -3, would get me to -2. And then dividing by my new exponent would be dividing by -2 or multiplying by -1/2. So it looks like I get -1 over 2x squared, right? Does that work? Plus c. And let's do a quick check on the second one. If I were to differentiate the second one just to verify, it was currently -1/2 x to the -2. If I were to differentiate that, I would get -1/2 times -2 x to the 1 less would be what, -3. And we see that the -1/2 times the -2, by golly, does cancel out to a +1. And my new exponent would be -3. So it works. Good. Good news, everybody. Good news. Math works. Oh. Gosh darn it, I was on the edge there for a while. We saw it the orient in the beginning. We could have gone either way. Sophia missed it. The whole conversation about Mr. Fritz maybe having a freak out moment. I'm going to hold off on that still. All right. So, question about 5b. That's pretty sweet. So what can get complicated? I'll reserve judgment on that. Instead, I'll let you and your partner come up with a strategy that you're going to use to tackle this, and then share with the whole class. So we're trying to mix everything up here, right? Put the different combinations and rules together, and then see what might be most appropriate. You guys got ready? You ready? Ready to share? You got it? You got a strategy? No? No for the back, yes for the front. So what are you guys going to use? Riley and Emily?
The natural log rule.
Natural log. Raise your hand if you're going to use natural log for this. Hey, you don't have to do polynomial long division because the degree of the numerator is 1 less than the degree of the denominator. In fact, it's there to act as, right, a portion of the denominator of this, the derivative of this quantity on the bottom to the first power, which makes it a natural log candidate. By golly, if I had 3x squared here, if we had 3x squared here, then this would go straight to natural log of quantity x cubed plus 1 closed bars plus c. But I didn't have a 3 on top. So what will we need to include in our antiderivative function? We'll have to cancel it out with a 1/3. So we'll need 1/3 natural log of absolute value bars of x cubed plus 1 closed bars plus c. That's pretty sweet. And look, we didn't need this whole bottom half of the whiteboard, so that's always nice. All right. Awesome. Great approach. Thank you. Great. All right. How do we want to tackle number 6 then? And so what does number 6 look like? Is this looking like the natural log again for number 6? So what are you guys thinking for this one? Do we have it? Sophia?
Would it be the half tan inverse of 2x?
Ooh, jumping all the way to the integrand. I'm sorry, all the way to the antiderivative. Yeah, we can't use natural log here because the derivative of my denominator, right, would include an x term in it, and I don't have an x. But this does look like 1 plus input squared on the bottom, which brings to mind an inverse tangent rule. Nice job, Sophia. And so if we could rewrite this like inverse tangent, then we'd be set. We know that the derivative of inverse tangent, right, is the derivative of the argument all over 1 plus the argument squared. So if we could rewrite this so that it looked like that, right? If we could write this so that it looked like inverse tangent, so I just flipped the order instead of 4x squared plus 1, I'm going to rewrite this as 1 plus 4x squared, and then I'm going to rewrite that 4x squared as an input squared. Isn't 2x quantity squared equal to 4x squared? And now, by golly, this looks just like inverse tangent, so long as I can provide for the derivative of the argument. In this case, what's the derivative of the argument? Well, the derivative of the argument, 2x, would be a 2. And if I had this, this would go straight to inverse tangent of 2x closed input plus c. But I didn't have the 2, so what do I need to include? A 1/2. And now we're complete. Nice work. So by rewriting that denominator, right, and making it look like 1 plus argument squared, we were able to utilize our inverse tangent rule that we already know. Isn't that sweet? Ha! Gosh, this is fun. I love integration. It's just like a puzzle. I was telling Sammy last week, like derivatives, while useful, kind of boring because they're just a procedure, right? We have a rule. Once we pick what the original expression rule is going to be employed, then we do it like a procedure. Integration, on the other hand, is a puzzle because we're not sure what rule necessarily needs to be employed. Sometimes we have to rearrange it and try to figure out what antiderivative function is going to be appropriate. So I like integration much better. All right, so can we use natural log for number 8? Can we split up that fraction?
Skip number 7.
Oh, sorry. I'm just excited. Well, I can ask the same questions. Can we split up the fraction for number 7? No, a sum or difference in the denominator, right? Can't be split up into a sum or difference of individual fractions. Can we use natural log? No, we don't have an x present. Well, we could provide a constant and cancel it out, right? With constant multipliers, we cannot include a variable there as part of the derivative of that quantity. So natural log is out. Polynomial long division, not going to work. I don't have another x term on top, right? And so what are we going to do? Well, if we could make it look like, right? If we could make it look like 1 plus argument squared, then we could utilize our inverse tangent. That's our only rule here that has, right, the derivative of 1 plus argument squared on the bottom. And we don't have, right, that derivative argument there, c, on top. The only problem is that inverse tangent always have a 1 plus argument squared. And right now I have 4 plus x squared. So what are we going to do? I harken back to my cooperating teacher's mantra, right? Some umpteen years ago when I was doing my student teaching in urban Tucson, Flowing Wells, Arizona. Factor first or fail, right? That was our mantra, factor first or fail. Can we factor that denominator and force it to be 1 plus quantity squared? Well, I think we can. If we were to rewrite this as, let's pull a 4 out. Let's factor out a 4. That would make this, well, 4 times what is x squared? 4 times x squared over 4 would equal x squared, plus 4 times what equals 4? 1, and there's our 1 plus argument squared. In fact, this 4 on bottom is simply a constant multiplier. I'm going to pull it out front entirely so I don't trip over it. Let's pull that out in front as a 1/4. And at the same time, let's rewrite my bottom as quantity 1 plus argument squared. What would my argument be, right? Such that when squared, it produces x squared over 4. What would my argument be? Kyle?
1/2x.
Absolutely. So I'll write my argument there as x over 2. So 1 plus argument squared would equal that 1 plus x squared over 4. That's pretty sweet. Now I can integrate this using inverse tangent, so long as we can provide the derivative of the argument. In this case, the derivative of the argument is 1/2. And if I had a 1/2, then I know this would go straight to inverse tangent of x over 2. Did I have a 1/2? No, so I'll need to account for that by multiplying the front by 2. There was already 1/4, however, so 1/4 times 2 over 1 is 1/2 inverse tangent of argument of x over 2, close argument plus c. That is pretty sweet. Thank you, Hayden. I'm glad we did this one first because, whoa. How about this one? Natural log. No x on top. Can't do natural log. Can't split up because the sum difference is not in the numerator, it's in the denominator, so can't split up the fraction algebraically. So we have to massage that integrand and make it look like a 1 plus argument squared. If we can make it look like a 1 plus argument squared, right, then we'll be good to go. It's just that we've got more than an x squared term. We've got an x squared term and an x term, right? This is usually the point in the lesson where I suggest maybe a field trip to Cocopelli. Seriously, what are we going to do with that? What are we going to do with that x term? Michael?
We like separate it to x plus 5 and x minus 1.
Ooh. Oh. X. Split up the 5?
Yeah.
Yes. That's exactly what we're going to have to do. We're going to split up that 5 so that we can group a part of that 5, right, with the x squared plus 4x and write it as an argument squared, and then have our necessary 1 there, right, our necessary 1 there for inverse tangent that the rule requires. So let's go ahead and rewrite this as x squared plus 4x plus, well, I'm not sure, but we have to have 1 for our inverse tangent rule, right? Don't we have to have 1 plus argument squared? And if I took 1 away from that 5, what would I have remaining? Well, we still have 4, right, remaining as part of that 5, and so that 5 is, well, it's right here. That 5 is 4 plus 1. And why? Is that helpful? It's not. Yes, it is. What do you recognize about the trinomial x squared plus 4x plus 4? It's a perfect square, right? It's a binomial squared. What quantity squared equals x squared plus 4x plus 4? Well, the quantity x plus 2. Isn't x plus 2 equal to? Quantity squared equal to x squared plus 2x plus 2x is plus 4x, and then plus 4? Yes, it is. And so by rearranging this, we've made it look like 1 plus argument squared times the derivative of the argument. Gosh, I hope we have the derivative of the argument enough there. What would be the derivative of this argument? Just 1 dx, and so we're good to go. Yes. Now we can go straight to inverse tangent. In fact, we don't have to provide any constants at all. That's pretty sweet. Thanks, Michael. We'll do inverse tangent of quantity x plus 2, closed quantity plus c. Gosh darn it. Oh, sweet. Huh. The math grand. And things are going so well, too. So that's not a perfect square. Binomial, trinomial, no x term. and inverse tangent has to be, right? Inverse tangent has to be 1 plus argument squared. But that's okay. We can make that look like, right? We can make that look like 1 plus argument squared. What would we have to factor out on bottom? Well, in order to make that a 1, we'd have to factor out a 16 on bottom. Let's try that. So we'll go ahead and factor out a 16, and that would leave me with, what, 9x squared over 16 times the 16 would equal to 9x squared plus 1, right? Isn't that right? So we can kick that 16 on bottom out front as a constant multiplier, 1/16 times the integral of, and we'll go ahead and rewrite that bottom with the 1 plus first, and if we can only make that look like an argument quantity squared, well, certainly. What argument quantity squared would equal 9x squared over 16? What's that going to have to be? Colin?
3x over 4.
Nice. So with the original input and my inverse tangent of 3x over 4, then argument squared equals that. Awesome. We're all set for an antiderivative so long as the derivative of the argument is present, and it's not. But the derivative of this argument is just 3/4. And so if we had a 3/4, right, then we'd have the derivative of the input, and we'd be able to go straight to inverse tangent of 3x over 4. But we didn't, so what do we have to do? We'll have to cancel out with the 4/3. There was already a 1/16 there, and so 4 over 16 is 1 over 4 times the 3 on bottom is, I'm getting 1/12. I'm getting 1/12. Inverse tangent of 3x over 4, close input, plus c. Dang, Greg. This is fun. Awesome. All right, go ahead and tackle this then with your partner. See if you can't find an antiderivative. I'm going to pause it and then call on you to share. Okay, so how did you handle the denominator in number 10? Right? What did you guys do? Maggie and James?
We split up 10 into 9 and
Okay, hang on, let me catch up. So Maggie says you guys split up the 10 into 9 and 1. Raise your hand if you did the same thing. 9 and 1 will make a perfect square trinomial, right? But it can be rewritten as argument squared, and then I've got my obligatory 1, right, for inverse tangent rule. Nice job. Thank you, Maggie. So let's go ahead and do a quick rewrite one more time. The antiderivative of, and let's do 1 plus my quantity now, right? What's my binomial going to be, Courtney?
x minus 3.
Awesome. Do we have the derivative of that argument present? Certainly, just 1 dx. So we can go right to my rule now. It appears as though the antiderivative is simply inverse tangent of x minus 3 plus c. And raise your hand if you have that already. So you have that already? Awesome, awesome. And we're close, right? So now we're mixing everything up, right? All stops out, could be anything, right? Could be anything. So what are you guys going to do for this one? Annika and Tyler?
Separate fraction.
Separate first and handle term by term. Nice. So if we were to rewrite this as split up a sum or difference, so first just x over x squared plus 1 plus, and then 1 over x squared plus 1, and integrate term by term, and Annika and Tyler have, right, rewritten that integrand in 2 different forms that we recognize. Now what rule overall will the first one be? Not the answer, just what rule will the first one give us? Marissa?
Natural.
Good. What rule will be our second one, right? What rule will be our second one? Grace?
Inverse tangent.
Beautiful. We can go right to it. If only I had a 2 there, right? Then we know this would come from a 1/2. 1/2 natural log of. And then straight up inverse tangent. Plus C. Pretty sweet. Awesome. All right, let's go ahead and close it up then. Please have a response that you're willing to share with the whole class. What strategy is appropriate when integrating a rational expression with quadratic denominator, linear numerator, or anytime the numerator degree is exactly 1 less than the denominator degree? Don't say it out loud. Go ahead and have a written response and be ready to share with the whole class. What if our rational expression includes quadratic denominator but a constant numerator? What rule do we have to work towards? What should we employ when the numerator degree is greater than or equal to the denominator degree? And lastly, what can we try when there's a sum or difference in the numerator? Okay, go ahead and share with the whole class what technique is appropriate or overall rule when the numerator degree is exactly 1 less than the denominator degree. Emily?
Natural log.
Natural log rule. Overall, we're working towards a natural log because we'll be able to provide the derivative of that denominator function. Nice job. Raise your hand if you have natural log for number 1. Natural log, good. Overall, quadratic denominator but a constant numerator, right? What are we going to have to go towards then? Hayden? Inverse tangent, absolutely. Then we're working towards an inverse tangent rule, right? Where I rewrite that bottom as a 1 plus quantity squared. What happens when the numerator degree is greater than or equal to the denominator degree? Right? What are we going to do then? Riley Freeman?
Polynomial long division.
Yeah, polynomial long division, then we'll see how we handle that. Polynomial long division. And lastly, if there's a sum or difference in the numerator, right, how do we handle that? Right? Marissa?
I wrote separate.
Yeah, we can separate it. We can break it up into a sum or difference of individual fractions, each with the same denominator. Individual fractions. Awesome. Thank you for sharing, you guys. So we've got AP Calculus Review Integration Worksheet. This has a mixture of different things. Don't think that each question relies on today's examples, right? They're just sprinkled in to keep you on your toes. The end of the year schedule, right, is up on Moodle, so you can check that out. Make sure you're bringing your Bellwork and activity stamps for next class. When we're done with our integration by parts lesson, you'll have a chance to work on your OTL just like today. I'm trying to make it so you have class time to work on your OTLs as much as possible. You still might have a little outside of class time work, but hopefully you'll have a big chunk of time to work in class. And then also you'll be getting part 1 in your review. If you're gone to the physics field trip for that Friday class period, make sure that you pick up the multiple choice part B on Wednesday. I just got them back from the copy center so that you have that at your disposal to work and study. You won't be missing any new class, right? New learning on that Friday, and you'll still be expected to take part 1 in that final exam, then the multiple choice part A upon your return on the 25th. So you want to make sure that you're letting me know if you're going on the physics trip and getting the part B. Questions about the end of the year schedule? Then you may work quietly together or individually on your review integration. I'll go ahead and stop the recording and upload it to our Moodle site.